we can have this counter circuit count in descending order, which means backwards. So we'd go from 3, 2, 1, 0. And all we have to do is just simply change the output from the regular Q to the not Q. See, the first circuit, my output was coming off of these pins. All I did here was change the output to come off the not Q output. And this alone is going to cause the counter to count in descending order and count backwards. So now the counter is at 0. When I press the button, it's going to be 3, 2, 1, 0. So instead of counting in ascending order, just like we did before, we're now counting in descending order. So that's all there is to it to switch the direction of count, whether count up or count down, just by changing the output. Now we're back to our main counter circuit. We have 4 flip-flops, so we're able to count from 0 through 15. And if you notice, the output is all taken from the regular Q output, while the not Q output is used to drive each additional flip-flop. As you could see, I write it here with my text. This is the decoder section, and this is the input that receives the code that you generate. Now, just as before, by using the output of one flip-flop to drive the input of the other, we can generate this sequence of signal here in binary. This circuit is a little different from the others because it resets itself whenever the code for 9 is present on the output. This detection is done by using this NAND gate here to detect whenever the code for 10 is present on the output, which means this go high and this go high, or you could see it here. This is the code for 10. Low, high, low, high. We should have a high here and a high here. And whenever we have 2 highs, then the output will go low. Now this low will reset the flip-flops back to 0. Now in the circuit, this flip-flop will be called the least significant bit, and this one the most significant bit. The least significant bit always changes state on every pulse. And you can see here, every time I press this button, this flip-flop always changes state. See, on every push of the button, it will always change state. And that is because it's normally low here, and when you press the button, it will go high. So every time you push the button, we will always have a transition on the least significant bit. This device is called a clock signal, and it's just a component that the simulator has that will generate a clock signal that we could use to test our circuit. It has one drawback to it, and that's the fact that you cannot control the frequency, so you can't speed up the signal or slow down the signal. So we just have to work with whatever frequency that this device has. So if I close this switch, the counter will receive a clock pulse signal. And there you have it. The counter is counting all by itself using the clock signal. So right now it's generating the sequence of binary codes, and whenever the code for 10 is detected by this NAND gate, the output will go low, and that output will reset all the flip-flops back to 0. And the reason why we reset the flip-flop to 0 after 9 is because we have one LED, and the LED can only display digit from 0 through 9. So even though the counter is still counting, we cannot use those extra digit after that. If we allow all that code to go to the decoder, the LED will just be blank and we wouldn't see anything. Now here's the same counter circuit configured to count in descending order, which means it will generate the codes from the highest to the lowest. Notice that only one output pin of the flip-flop is used, and it's the Q output. See, all the NOT output is not used, so I'm only using one output of the flip-flop. Now here's a counter circuit that uses integrated circuit counters instead of individual flip-flops. In this particular circuit we have two digits. This is our least significant digit and this is our most significant digit. For this we need to have two counters and two decoders. So this counter and this decoder control our least significant digit, and this counter and this decoder control our most significant digit. Now the way how it works in counting is that the least significant digit is going to go from 0 through 9, and then when it resets to 0, this digit is supposed to go to 1, and then we will have 10. When this digit reaches 0 again, this digit will go to 2, and we will have 20. To achieve this effect, we place a 4-input NOR gate on the 4-bit bus between the first counter and decoder. The output of the 4-input NOR gate will only be high whenever the code for 0 is present on the input. When we start counting, the most significant digit will not increment right away, because the counter only reacts on the positive edge of the signal, that is, low to high. Since the clock input of the counter is currently high, only when the output of the NOR gate goes low, then back high, will the counter increment. This means that only after we complete the first cycle of the least significant digit will the counter increment. If we had used an OR gate instead, it would cause the most significant digit counter to receive a transition of low to high on the first pulse of the main clock signal. We would see this as 11, 12, 13, 14, etc., instead of the counter counting from 0 through 99. This counter received the main clock signal, and just as before with our flip-flops, these counters react to low to high. So whenever we press the button, this counter will react and this digit will increment. Now the output of these counters have what's called a carry output, which whenever the counter reaches 9, this pin will go high. Now this counter, on the other hand, is driven by this 4-input NOR gate. Whenever 0 is detected on this bus, the output of this NOR gate will go low. Whenever it goes low, nothing happens to the counter right away. It don't react, because it reacts from low to high, positive edge. However, when it switches back to low, this counter will effectively see a low to high transition and cause this digit to increment by 1. So the only time this counter will ever increment by 1 is whenever this one completes a cycle from 0 through 9. This button is the lamp test button. Whenever it goes low, it will light up all the segments in the LED. As you can see. Whenever the counter reaches 9, this carry output goes high and we have the LED light up right here. Now when we make another pulse, it's going to reset itself and go back to 0. At this time, this carry input is going to go back low, so the LED is going to be off. And at the same time, this counter receives a sequence of low to high from the output of this NOR gate, and this counter receives 1 pulse as a result and change this digit to 1, while this one is going to cycle back There we have it. So basically the counter will just continue to do the same thing. Whenever this digit complete 1 cycle, this one go up by 1. And that's the way how we count. Okay, stop it right there.